Everyone, so we're going to continue on and we're going to do the second question in the 2019 AP Physics C test. This is going to be set two. So this is the conservation of energy questions. So let's see. With part two, they have this rocket being shot up, and they give us the acceleration function, and they want us to figure out what is the net impulse on the rocket. Like always, make sure that you attempt these questions first. The link to the description will be in the description below. All right, so what I can do is if you look on the reference table, the equation for impulse is given as the integral of f with respect to time. I can actually rewrite this so that it's mass times acceleration with respect to time, since I have the equation for the acceleration. Since the mass is constant throughout, I can actually pull it out of the integral. And now what I'm going to do is I'm doing the integral of k minus lt squared with respect to time. So take it one part at a time. K is going to end up being, well, when I do k, it's going to end up being k times t. I'm just going to add a t onto it. For this one, it's going to end up going from, let's say, L. I'm going to add 1 to the exponent, makes it a 3, divide this by 3, and I have that. Now, one thing I did want to point out, they mentioned that they want us between 0 and 6 seconds. So my bounds for this should be 0 to 6, and this should be 0 to 6. So now what I'm going to do is I'm going to put the final time in and put the initial time in and subtract those numbers. So m times 6k minus L over 3 6 cubed. And this is going to be minus, I'm actually going to put this all into a bigger bracket, 0 minus 0. Easy enough. So that later part ends up dropping out. So what I can actually also do is plug in the numbers. So my mass is going to be 0.5. K is going to be 9. L is 0.25. 6 cubed over 3. So let's figure out what this is. 6 times 9 is going to be 54. Divided by 2 is going to be 27. For this, 0.25 times 6 cubed divided by 3 is 18. Divide that by, I was going to say divided by 0.5, but divided by 2 gets us 9. So 27 minus 9 is 18. So my impulse is 18, let's see, Newton seconds. All right, so this was a 2-point question. So you got 1 point for essentially doing this top part, and then 1 point for all this stuff. Now, there was actually a second way to do this. Another way of doing impulse is by doing just change in momentum. So if you figured out what the final velocity was and subtract it from the initial velocity, you would end up getting your answer. Now the initial velocity is 0, so that actually can be dropped out. So realistically, this was also equal to m times the final velocity. So you could have used this to figure out what the velocity was at some point. You would have actually still had to do the integral. You would have had to do the integral of the acceleration though. in order to figure out what the final speed is. That's pretty much it. Um, but again, either way, you ended up having to do an integration. All right. So for part B, uh, now this is actually there's two different ways of doing this. So if you recall, I had just mentioned that if you had done an integration of the acceleration to find the velocity, then you could have used that velocity in here to find the impulse so that you didn't have to do an integration again. Um, the same thing pretty much is true for B. There is actually, now that I have the impulse, I can then say that. I can say that the impulse is equal to delta P, which is equal to M final velocity minus initial velocity. The initial velocity is 0. Solving this, I end up getting, what is it, 18 equals 0.5 times V, divide both sides by 0.5, and we end up having uh, V equal to 36. So what this really means is that to get A and B, one of those questions had to include integrals. You could have either done the integration of the acceleration for part B and then used the basic equation, the AP1 version of the equation, of the impulse equation to find what this impulse was, or you could do the integration for impulse in part A and then use that in part B with the same equation, just solving for something different. Or if for some reason you didn't like either choice and you want to do integrations for both, that's also fine. To do that, it's this. So basically we're doing kind of the same thing except without the m. So it would have been between 0 and 6. You would have done v is equal to the integral of k minus lt squared, yada yada yada. And like I said, it's the same thing except you just don't put that 0.5 in there. All right. Part C. Okay, so part C, it wants us to find the kinetic energy of the rocket at 6 seconds, and then the second one is the change in the gravitational potential energy between those 2 points. So let's see. I guess we'll do this first one. Well, obviously, we'll do that one first. This one's pretty easy. Don't really need to go into too much detail with that. I already know what the speed is at 6 seconds. So what I'm going to do is k equals 1 half mv squared. 1 half of 0.5 times 36 squared. So that's actually kind of 36 squared divided by 4, which is really just 324 joules. I should point out back here, this was a 2-point question. So you got 1 point for essentially the equation, 1 point for the answer. Similar thing here. If you ended up doing calculus, it would have been 1 point for this setup, 1 point for the answer. This one was also 2 points. You got 1 point for pretty much using this equation, and 1 point for the answer with the substitution. All right, going back down to here. So they want the gravitational potential energy of the system between 0 and 6 seconds. Now here is actually something that is pretty interesting, or an interesting thing to note. So if you notice, part A has the impulse between 0 and 6 seconds, while B and C, I, are at 6 seconds. The reason they do this a lot, when they give you a range of values, that's usually because they want you to do an integration, or at least you need to do an integration. And then if it's just at some point, you don't normally have to worry about it too much. So what that kind of means is, in order to find this change in potential energy, which is going to be equal to mgh essentially. I need to figure out what the equation is for h. So I need to do an integration. I could do the integration of the well, technically I would have already done the acceleration for the integral for the acceleration, so I can actually piggyback off that. The velocity. Let me actually change this up. The height is going to be the integral of velocity with respect to time. My velocity equation is this part before I substitute in the 6 and 0. So that's going to be kt minus lt cubed over 3. With respect to time. And this is going from 0 to 6. Alright, so when I integrate this, I add 1 to its exponent, so that's 2. Divide the k by 2. Add 1 to this exponent, that's 4. Divide this entire thing by 4. Since there's already 3, I'm multiplying them, so it's going to be 12 t to the 4th. And this is going to be evaluated between 6 and 0. So over here, I'm just going to plug it in. So this will end up being, I guess, let me plug in the numbers. So k is 6. So this will be 6. Actually, no, you know what? I'm going to do it. 6 divided by 2 times by 6 squared minus 0.25 divided by 12, 6 to the 4th. And then when I plug zeros in for this entire thing ends up being 0. So my height is going to end up being 6 times 6 squared divided by 2. That will be 108. 0.24 divided by 12 times 6 to the 4th. This will end up being 25.92. I'm just going to actually double check that. Okay, actually I did make a mistake there. I accidentally used a 4, so that's 27. So doing this together, 108 minus 27 gets me 81. I can plug it back into this equation. So mu g is going to be equal to the mass times gravity times 81. So that's going to be 405 joules. All right. Actually, I just realized I made a complete mistake right here. That's a 9. I accidentally looked up here and saw the 6, and I thought that was the k. So let me actually redo this math. 9 times 6 squared divided by 2 minus 27 135. So times this by 10 divided by 2, and I end up getting not 405, but I get 675. Now you may have something slightly different depending on if you use 10 or 9.8, but that's pretty much what you'd end up doing. This was a 3-point question, so you got 1 point for essentially doing this. This entire integration, there was 1 point for evaluating with the 6 seconds, 0 to 6, and you got 1 point for plugging it back into the potential energy equation. So these were the 3 points that you got for this. All right. Now scroll over to part D. Part D says find the max height reached by the rocket relative to the launching point. All right, so let's see. It says that the upwards acceleration during 6 seconds is given by this. Then after the 6 seconds, it basically continues up like a projectile. So we're going to treat that as a vertical projectile. It ends up, it had an initial velocity of 36. Was that what I ended up getting before? It's hard to read my handwriting right now. And it's going up to its max height, where its final speed is going to be equal to 0. So I can use the timeless equation. Solve for the distance. Actually, I probably could have used energy too if I wanted, but I'm doing this anyway. So the distance would have been the final velocity divided by 2a. This 36 squared. It's being affected only by gravity, so this is going to be 2 times 10. So 36 squared divided by 20 is essentially 64.8. I'm just going to round that to 65. That's not my final answer. I actually have to add that to the height gained during that initial 6 seconds. So my total height is going to be 135 plus 65. And that ends up being 200. All right. Now, this was 3 points. You got 1 point for doing this. 1 point for substituting the numbers in. And essentially 1 point for adding in the initial height that you got from before. As I mentioned, you could have used energy instead. The way that would work, or the way that would look, it would look like this. We're trying to find the potential energy. So actually, we could have done the whole thing together. So we could have done the final potential energy is equal to the potential energy at that height plus its kinetic energy at that height. So this would have ended up being mgh would have been the total height plus mg whatever height it was during the first 6 seconds plus the 1/2 mv squared during that 6 seconds. Mass drops out. This is going to get the g. I'm dropping out a g from both terms, so I'm dividing g by everything. So my total height would have been equal to the initial height plus v squared over 2g. You actually can see right here that it's the same thing I got here, v squared over 2a, v squared over 2g, plus the initial height, and then we would have gotten our answer. So 135 plus 36 squared divided by 20, yada, yada, yada. So you can already see that I would have gotten the same answer. Once again, you would have gotten 1 point for pretty much this entire line, 1 point for substituting the numbers in, and 1 point for the answer. All right, let's go to the last question, or last part, part E. They give us this graph, and they want us to sketch the velocity as a function of time. And they say that t top is where it's going to actually reach that max height. Let's see. So once it reaches its maximum height, we know the velocity has to be 0. So we know that this ends up being 0. We know it starts at 0. Like that. And let's see. We know it stops accelerating. Well, so it's accelerating here. And we know that it's going to end up reaching some max velocity of 36, because that's pretty much that's how the equation works. What I'm going to do is I'm going to draw in a essentially a maximum line. So let's see, can I actually change the way this looks? There we go. So this is going to be essentially my max line. Um, I know that once it reaches this, I don't know exactly when it's going to reach it, but I don't think it matters. Oh, that is not what I wanted to do. Let me undo. It's going to go straight down. And this slope, you don't need to note this, but this slope actually will end up being equal to the acceleration due to gravity. Um, so the only thing is, what is this going to look like? What is this section going to look like? What you can do, since you have a graphing calculator, you can actually plug in to your graphing calculator. We know that the equation for the line is going to end up being um, velocity is going to be 9t minus t cubed over 12. So you can actually plug that in and see like what the graph looks like. It doesn't need to be perfect. What you probably would end up doing is, since this is a t cubed graph, it's going to look like this. It's going to go down, it's going to go up, and then it's going to go down again. This will be the y-axis, this will be the x. It's going to go up like this. Now, the reason we know that it's going to keep going up like this, we actually look at the acceleration. At 6 seconds, it is still accelerating up. So the velocity should be constantly increasing, but it should definitely be curved and going down, because as time goes up, this section increases, meaning that the entire acceleration decreases over time. So this is what the graph will end up looking like. You're going to end up having 3 points for this. You'll end up having, let's see, 1 point, 1 point for doing this segment, a line that starts here and then ends up essentially being a concave down curve. You have 1 point for basically recognizing that at some point it's going to go straight down in a linear line through T top. You'd want to make sure that it actually does cross over that line. And then you get 1 point for what looks like, looks like having the max value being equal to whatever you got in part B, as well as having it cross at T. So those 2 points were all wrapped up into this 1 point. So this was question 2. For the most part, not super difficult. Like I said, there was pretty much only one question that I could, two questions, sorry, 2 parts that required integration. But again, there's always you'd at least be able to get partial credit. And even if you bombed the sections with the integrations, or at least didn't know how to do the follow through, but attempted something, there's a good chance that you probably would have walked away with. I think the entire question is 15 points. Yeah, you would have been able to walk away with at least 10, maybe even 12 points, even if you completely botched these integrations. All right, so if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.